I'm now going to show you how to use Wolfram Alpha to do some regression analysis. Regression is like when you're comparing X and you're looking at X values and Y values to see if there's a function or a relationship between them. So as X increases, does Y increase or decrease type questions. A lot of time you'll take data in your field and say, hey, are they related? Let's look at a regression. If they are related, there's ways to compute them statistically to see how strong is the relationship. So I'm just going to click on the examples, and specifically I'm going to go into the statistics and data analysis pane, and I'm going to look at this thing called regression. And here they give you an example. Are they linear related? Meaning as one goes up, as X goes up or down, does Y go up or down? And the way Wolfram Alpha wants you to enter the data is, here I'm looking at a linear fit. And curly Q of 1.3 comma 2.2, that's an X and Y value of the first data point. Put a comma. Then another curly Q, 2.1 comma 5.8, close curly Q. That's the X and the Y of the second data point. And repeat it for third data point, fourth data point, fifth data point, sixth data point, seven, on and on and on you go. And we're going to go look at this data and try to see if there's a linear fit, a linear regression we can analyze for this data. See if the data points are related. And what Wolfram Alpha returns me is the regression analysis of this data, a fit. I'm looking at a linear function of this data up here. Are they related? And because it's linear, it's y equal m of x plus b. So here, 3.1938 is the slope of this line. Here's all the data, the x and y data plotted. If you were to plot each one of these data points up here, you'd plot them on a graph, an XY graph that looks just like this. Let me blow that up a little bit. So if you plotted each of the data points, you'd get a graph that looked like this. And this linear fit line is the linear function that best fits this data in a regression type analysis. And one of the big things you look for in regression is this R squared term, 0.98. The closer that gets to 1, the better the fit. So yeah, this data is related to each other. Whatever variable X is and whatever variable Y is, the X and Y are related to each other. Here's the data points plotted, each one of the data points. And then here's the fit of the linear line through it with a strong R squared value. Now, if you said, you know what? It looks kind of like that data is not really linear. It almost looks like it's some kind of like a quadratic or some other type of a function. So you could literally go in here and say, you know what? I don't want to look at a linear fit. I want to look at a quadratic fit. Notice it was 0.9897. Now let's look at a quadratic fit. Remember that R squared, 0.98977. Now we're going to fit a quadratic function rather than a y equals mx plus b. And we come down here and we say, hey, the data is fit by y. The best function is y equal to a minus blah, 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 x squared plus blah, 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 x minus 4.6. That's kind of a quadratic. And now I'm getting a little bit tighter fit, 0.99608. And there's the quadratic function. Notice how it has curves. So a lot of times you're going to get data. You're going to collect it out there in the field at your job. You're going to plot it on an XY graph and say, hey, does it look like it's fitting a linear, which is the slope equation, y equals mx plus b? Or does it look more like a quadratic, an x squared plus an x term plus a constant? And in this case, it's a little tighter fit. But trust me, the linear fit is a good one too. I just wanted to show you the difference between a quadratic fit, with the resulting correlation coefficients. That's what they call these R squared terms. How tight is the fit? And it gives you the function of the curve. So very powerful little handy tool to analyze your data.